Hi everyone, this series of videos is intended to introduce the Analog Discovery Board and the Waveform software. I'm Professor Ram from the Engineering Department at UMass Boston, and I also run the Ubiquitous Communications and Networking Lab, or UCAN Lab. In this video we will introduce the AD2 board's scope channels and the scope tool in waveforms. We will demonstrate how to use these tools to measure signals that are created using the AD2's waveform generator, but we could just as easily use the scope to measure other external signals that are not generated by our AD2 board. Again, please note that you can find much more detail about these tools in the digital reference documentation shown here at this link. Coming back to our AD2 pinout, we're going to use the waveform generator to create a signal just like we've done in previous videos. However, we will also be using the scope channels to measure the voltage differential of an external signal or a signal from our AD2 board and observe this measured signal. We can notice that our AD2 has two scope channels. When observing channel 1, we're going to measure the voltage difference across the 1 plus and 1 minus pins. And similarly, channel 2 measurements are observed as the voltage differential across our 2 plus and 2 minus pins. In waveforms, we'll now be using two of our tools. The Wavegen Tool will again be used to define our generated signal, and we're also going to introduce the Scope tool, which we will use to observe the acquired signal or signals from our scope channels. For our first look here at scope channels, we're simply going to demonstrate the direct connection between our channel 1 of our waveform generator and the scope's channel 1. Looking at our actual hardware, we can see that we've done this using one of our male header pins, and in this case we've connected our W1 pin directly to our 1 plus of our scope and our ground pin to our 1 minus of the scope. When we open up waveforms, we're going to start our Wavegen as usual. And if we observe our highlighted tab in the top menu, we see that we go from our Welcome tab to the Windows tab when we open this Wavegen window. This tab basically gives us a container where any open windows are going to show up, right? This Windows tab here. If we want to open a second window or tool, we can go back to our Welcome tab and then, for example, open the Scope tool. We can now see that we have a scope in this top window and our Wavegen window in this bottom window. This default view is probably good for many applications, but waveforms is also pretty flexible in how we move these windows around, and we'll find that organizing our windows will sometimes help us to see what we're working on a little bit better. I often find that students are worried about changing the environment too much, specifically when they're working on a project, just because they're concerned that they might impact their experiment. So I strongly suggest that you take some time in advance just to familiarize yourself with some of the more non-technical aspects of this environment that you're going to be working with. In these two windows here, we can drag and drop to move things around just by clicking on the heading for a specific window. For example, here we'll click on the heading for our Wavegen window, and we can see that as we move it around, the preview changes of where it'll go. In this case, we can move over here. We can also click on the border between our two windows to resize either one of these windows. We can also change our view here so that each tool has its own tab by coming up here to our main bar and selecting this multi-tab icon up in the top right here of our Windows window container, or Waveforms Windows container. Right? If we look at this now, we have a tab for our scope and a different tab for our Wavegen. If we want to go back, we can come back over to the right here and select on this stacked tabs icon. If we want to take this view outside of the waveforms container, right, this Windows container, we can also select the pop-out tabs for each of our windows or for a specific window by looking at a window, for example, this scope window, and selecting this pop-out tab. Now we have a separate scope or oscilloscope window that shows up in our list of different windows here. If we want to view from outside this container, we can also select this, and then we can close windows individually by selecting the X either here in this open window or in the window within our container here. If we want to get that scope back again, we can also go back to our Welcome tab, but just for simplicity, rather than going back to the tab, we can click on this plus button and we'll see a drop-down menu where we can select scope just to reopen that scope that we've already seen. So coming back and bringing this back to where we were before with the two windows aligned side by side, we have the signal that we're going to generate on this left side here, which is going to be sent out to our AD2 waveform channel. And then on the right we have this scope window where we're going to show the signal or signals that are being acquired by our AD2's scope channels. If we come over to our scope and we click Run, we'll see that our scope channel is currently measuring relatively constant 0 volts. This is because our Wavegen is showing the preview of our signal here. It's the preview of what we will be sending, but we haven't actually started sending this on our waveform channel because we haven't selected Run on the waveform yet. The scope is actually showing our measurements from both channel 1 and channel 2 right now by default, and we can see this by looking at this panel over here to the right. We see that channel 1 and 2 are both enabled with these check marks, and that channel 1 is shown in yellow, indicated by the border around this channel 1 information, and channel 2 is indicated by blue, indicated by this border around here. Now, although the signal on channel 1 is covering up this channel 2 right now, if we select the check mark on channel 1, we'll turn off the channel 1 view here, and we just see this blue signal representing our signal on channel 2, which is also that relatively constant 0 volts just because it's not connected to anything. If we come back and select on the check mark next to channel 2, we've again turned off, we've now turned off channel 2 and now turned off both of our signals, so we no longer see anything on our scope. Since in this case we're only interested in channel 1, since we've only connected our waveform generator channel to our scope channel 1, we'll come back and re-enable channel 1 here. And now if we go ahead to our Wavegen tool or on this left window and select Run, we'll now see that the signal on channel 1 of our scope is actually showing up as we transmit this signal from our waveform generator channel and receive it on our scope channel. Note that that transmitted signal here has a 1 volt amplitude. Right? We've specified 1 volt here. We can see this as -1 to 1, showing our 1 volt amplitude. And we also see this on our scope's range. Right? So our scope, the signal that's received on our scope, because we've directly connected this, has an amplitude of 1 volt as well. Right? Showing up here with our axes labels on the left. Our current setting here on the scope is set to 500 millivolts per division. If we look over in our channel parameters, and we can see this by each one of these blocks here representing 0.5 volts or 500 millivolts. So we have 2 divisions above 0 representing this 1 volt peak of our signal or amplitude, and two divisions below 0 representing this -1 volt at the minimum. Let's start here by observing what happens when we actually change the resolution of our scope. Right? Changing our scope's amplitude resolution for channel 1 to 1 volt per division, we can actually observe that this changes how the signal is viewed on the scope, but keep in mind that we still have an amplitude of 1 volt. Right? So now our peak is 1 volt, our minimum is -1 volt, and we still have the same signal, this sine wave with a 1 volt amplitude. Similarly, we can change the resolution of our scope's time axes. And our transmitted signal has a 1 kilohertz frequency, what we've sent from our Wavegen, and we can see that this has this 1 millisecond period of our single period of our sinusoid, which we can observe in this Wavegen preview. And since our scope's time axis here has a resolution of 1 millisecond per division, we notice that each division here has a single period of our sine wave. Right? One here, one here. Between 0 milliseconds and 1 milliseconds, we have one period of our sine wave, and so on. If we change this resolution to 500 microseconds per division, we can see now that the division again changes the way that the signal is viewed on our scope, but we still haven't actually changed the generated signal. So we still look here and we can see that a single period of our sine wave is 1 millisecond, or in other words, 2 divisions in our scope view. If you have a mouse with a scroll wheel, you can actually change the time axis pretty easily just by scrolling up to increase the time per division, or scrolling down to decrease the amount of time per division. If we go back to our Wavegen, we can now modify the actual signal that's being generated and observed. If we change the type of our signal here to a square wave, for example, we can see that the new waveform shows up in both the Wavegen preview and in our actual observed signal on our scope. Note that the scope here is actually being periodically updated with a new set of data points. So if we look in our Options tab, we can see here that it's updated every 10 milliseconds. But we can actually reduce this update frequency if your computer is a bit older and maybe can't keep up with the data coming in. We can select this here and change to something like every 100 milliseconds or 500 milliseconds or so on. If we want to hold a single snapshot of our observed signal, we can use this single button in the top left of our scope window. So selecting this, we freeze a single snapshot of our signal of interest, or our observed signal. So we can notice now if we go back to our Wavegen and we change this back to a sine wave, our updated signal is shown in the preview. This is still being run and now transmitted on our actual waveform signal, but if we look at our scope preview, we see that the previous square wave is still there and still seen in our scope because we captured that single snapshot and sort of froze it in place here. If we come back over to our scope and now just click Run again, we see that this sine wave is now being observed as the actual signal that's being sent. If we go in and change our signal's amplitude of the actual transmitted signal from 1 volt to, say, 100 millivolts, we can see that our preview changes. And we get this range here, and we can actually see that our observed signal on our scope is updated as well. Right? In our scope here, we see that our amplitude is reduced, but we've kept that same resolution from before as 1 volt per division. Right? So we're still observing with the same resolution, but the signal, the actual generated signal, has reduced its amplitude. So it's a bit harder for us to see this signal here. Of course, we can go back into our scope and change our resolution of this channel 1 to, say, 100 millivolt per division. And now this gives us this better view of the signal that we're actually observing, keeping in mind now that our amplitude here has a peak of 100 millivolts and a minimum of negative 100 millivolts. We can follow a similar observation for our time scale. So if we go in and change the period of our signal to, say, 100 microseconds in Wavegen, we see the updated frequency goes to 10 kilohertz. Right, we can observe our preview in the Wavegen. Our axes, our time axis here is changed to 100 microseconds for our preview. And now if we go back to our scope, we haven't actually changed the way that we're observing the signal, so it's obviously more difficult to see this higher frequency signal. Right? We see a lot more periods of our sine wave as we look through this higher frequency signal with the same resolution that we had before. If we zoom in here by changing our time resolution to 100 microseconds per division, we can now observe the signal similar to before with a single period in each division, right? Just as we've shown previously, except now each division represents a smaller period of time, or for example, 100 microseconds. We can move the 0 point around with this arrow at the top here too, just to help visualize things a little bit, right? So from 0 to 100 microseconds, we see one period of our sine wave, which makes sense because the newly generated sine wave is transmitting at 10 kilohertz. You should also note that there are some limitations to the rate that our AD2 hardware can actually operate. And we'll cover this in more detail in a future video, but we can start to see this if we change our signal, for example, to a 1 megahertz square wave. And we can go into our scope and zoom in a little bit to observe this at this higher resolution. You can now see that our signal is not nearly as crisp as what it was and what we were looking at previously. If we change our signal to a 10 megahertz signal, we see a little warning icon next to the frequency. And notice that our observed waveform no longer really matches that square wave signal that we were looking to transmit here. So just being cautious of these higher frequency signals based on the limited capabilities of this AD2 hardware. So this wraps up our basic introduction to the scope functionality of the AD2 board and the waveform software. There's quite a bit more that we can do with our scope and waveforms, and we'll cover some of the additional functionality in future videos. The main thing to keep in mind here is that the settings that we change in the scope change how we are observing the signal or viewing the signal, but they don't actually modify the signal itself. On the other hand, the Wavegen tool is actually used to modify the signal that we're creating.